Okay, let's get started. Welcome to the Simons Institute. My name is Venkat Guruswamy, and I'm a senior scientist here at the Simons Institute for the Theory of Computing. For those who might be, watching and may not be familiar yet, the Simons Institute is the leading international venue for collaborative research on theoretical computer science, and it brings together the world's leading researchers in theory of CS and related fields, as well as the next generation of outstanding young scholars every semester. So it was started with a generous grant from the Simons Foundation in 2012 and is just entering the second decade of its programs. So typically the Simons Institute runs 2 programs each semester, each of which brings around 70 long-term visitors, junior or senior, to Berkeley. And the scheduled programming of each of these thematic semesters includes a boot camp as well as 3 workshops spread through the semester, and for which additional visitors come to Berkeley. And it's my pleasure to welcome you to the workshop on epidemics and information diffusion, which is the second of 3 workshops in this semester's program on graph limits and processes on networks from epidemics to misinformation. So I would like to sincerely thank the organizers of this week's workshop for their hard work in putting together a great program. So they are Abba Gumel, Malvina Lushak, Mohammad Akbarpur, Amin Saberi, and Alessandro Vespignani. And thanks to all of them. And I'd like to cover a few logistics for the coming week before handing it over to Abba for the introduction to the workshop. So food is provided before the first talk and in the breaks, and it's just outside the auditorium here. For lunch, you're on your own, but there are many great options nearby in walking distance. And we ask that you please leave any food and drinks outside the auditorium and just consume them in the breaks, but not bring them inside. And if you have any AV issues, Omiyat Far is always around to help speakers get set up. And also a reminder that all events in Simons Institute are live streamed. So this workshop is also live streamed, so anyone can watch worldwide. And finally, a special thanks to our events team who are key to putting all these programs together week after week. So that is Kelani Penland, Ashley Hassan, and Elizabeth Yuen for managing all the logistics both here as well as things like accommodation for out-of-town visitors. So big thanks to them. With that, I'll now hand things over to Abba to introduce the workshop.
Thank you very much. And yes, welcome all to this second of the series of events lined up under the program on graph limits and processes on networks from epidemics to misinformation. So we welcome you all. My name is Abba Gumel. Was at Arizona State University, recently moved to the University of Maryland. So the workshop is on epidemics or information diffusion. So the second, we had the boot camp last in August, I think August 29th to September 2nd. So this particular workshop brings together a multidisciplinary team of researchers from computer science, from mathematics, from epidemiology, from economics, public health, and to come together to address important problems associated with the spread of diseases on social networks and also the spread of information, misinformation. So that's the purpose. Some of the themes of the conference to conduct a rigorous analysis of processes which model the spread of infectious diseases or pathogens in a social network, but with the main goal of developing predictive models, very high quality predictive models, as well as effective public health policies and algorithmic solutions for the control and mitigations of those diseases. So that's the main theme of the conference. This also entails epidemic models used to study and model the spread of new ideas, new technologies, information and misinformation. As mentioned, organizers Malvina Lushak from University of Melbourne, Mohammad Akbarpur from Stanford. The last 2, they deserve special mention. So Amin Saberi right here, and also Christian Boff. So others 2, this will never ever happen. I mean, even though they are the main pillars for all of these events. I mean, it's amazing how much they work, how much time they put into all of this, and just how very efficient they are. So I'm very thankful to all the co-organizers for this, but specifically Amin and Christian. We're thankful also to the Simons Institute for the support and also for administrative support. Elizabeth Yuan has been fantastic, the Associate Events Coordinator. Also Christian Wang, Sunday Irani, the Deputy Director, and so on. So we have a series of exciting lectures lined up, and we'll start the very first one today. And I think for those of us in mathematical epidemiology, Tom Britton requires absolutely no introduction whatsoever. This is his name, and I didn't prepare any slides to any write-up to talk about his background, because it's a name that is very well known. But the talk today is on epidemic models with manual and digital contact tracing. But I should also mention one of the amazing work done on the modeling of COVID-19 in the last few years, I think was his paper in Science that talked about how complicated the notion of herd immunity is when you incorporate heterogeneities in, and that's great to read. And anyway, so it's my great honor to welcome Tom Britton from Stockholm University in Sweden to give the very first talk for this session.
Thank you for the nice introduction. Thanks for inviting me to this nice workshop and staying here for several weeks. I'm enjoying it very much, both scientifically and also the surroundings are very nice to see as well. So I don't think I will use the full hour, but we will see. So please interrupt me if there are questions, because I don't have all that much to say, I would say. Anyway, I will talk about contact tracing. I will introduce both manual and digital. So digital is the contact tracing through these apps, but in a modeling perspective. So it's not that I'm analyzing data or anything. So this is joint work with a PhD student of mine. So well, in her PhD thesis, and our ultimate goal is quite ambitious. We would like to consider both manual and digital contact tracing. We don't want them to be perfect in the sense that not all manual contact tracing are able to reach the contacts, and also not everyone is using the app. Also, we would like to have sort of two sorts of contacts: random contacts in the community at large, but also contacts taking place on some social structure. It could be a network or households or whatever. So we would like to have sort of one rate at which you mix with people in the population at large, and another rate at which you meet with your day-to-day friends or something like that. So that is what we were aiming for. And maybe I should have had this taking place. So think of a situation where you meet people at random, maybe people on the bus or in the shop or something, and you are at risk of infecting others or getting infected, but also you meet your friends that you meet regularly. If you were diagnosed and being asked to who have you been in contact with, probably you would know the ones, your friends that you've had contact with, but you wouldn't be able to say, yeah, I sat next to, well, you don't know who you sat next to on the bus or who you met in the zoo. So when you manually contact trace, maybe that only takes place on the socially structured situation, but not among the random contacts, whereas the digital contact tracing works in both situations. Also, we would like to have a delay between, so suppose I'm diagnosed, test positive today, and probably it's not that immediately I am questioned for who have I been in close contact with, and they would be reached immediately. So probably there's a few days of delay. We would like to introduce that into the model as well. And also, if I name my friends, or in the digital app, they are warned. If those people are test positive, usually they go test themselves. There's an additional delay, and if they test positive, also they would be contact traced for their contacts. So the contact trace happens iteratively. All this is what we would like to do. However, we haven't succeeded. So yet, at least. So we don't consider, so far, we haven't considered infections on a network or anything. So we just look at homogeneous contacts. Unfortunately, but this is something we're working on right now. I'll say a few words at the end, but we have no delay. And I think that's the most, all models are wrong. Some are still useful, as Box once said. But I think this is the biggest disadvantage with our model. So if I'm test positive in our model, the contacts that I have, I will name them immediately and they will be reached immediately and tested immediately. So that's not very realistic. We do consider iterative contact tracing. Probably if someone, if I mentioned that I've been in close contact with these 5 people. If 2 of them are tested and they are currently infectious, they would be contact traced. Maybe one was recovered maybe last week. Maybe that one would also be contact traced, but someone that tested that was infected 5 weeks ago probably would not be contact traced. But we assume that we contact trace everyone who has been infected. So maybe you can think that it's both a testing of the carrying viruses, but also an antibody test, and also the one having antibodies would be contact traced. Not fully realistic, but that's what we have. I will come back to the model later. And well, we don't have any social structure, so for that reason, we will not. This point is not relevant to say. And we focus exclusively on the initial phase of the epidemic. So that's the situation we have managed to treat so far, and we are working on introducing a delay between being diagnosed and successful contact tracing. So a few words about the epidemic model. First, about the general epidemic model. I'm assuming most of you guys know epidemic models, but still, let me say which one I'm considering. So it's a stochastic SIR epidemic. I'm looking at the finite and fixed population size n, and I'm looking at the situation where n tends to infinity. I assume homogeneous mixing, and also I assume that the model is Markovian. So the model says that we infect any infectious person has infectious contacts at rate beta during your infectious period. So it's not the time varying infectivity or anything. It's a constant infectivity rate beta. And each time you have such a contact, so this follows a Poisson process with constant intensity. And each time you have such a contact, it is with a uniformly selected individual from the population. So there's no population structure. And if you have contact with someone that is susceptible, that person gets infected. If you have contact with someone that has already been infected and even perhaps recovered, the contact has no effect. And so that is a rate beta, and the other parameter is that infectious individuals recover at rate gamma. So this is the Markovian assumption. I think we will hear talks today where this is relaxed. So you have maybe a general distribution of the infectious period, but I'm assuming that it's exponential. And all these things are defined to be mutually independent. We start with everyone being susceptible except one index case. And this epidemic goes on until the first time when there's no infectious individual, and then the epidemic stops. For this model, it's well known that the reproduction number is the infection rate multiplied by the duration, the average duration of the infectious period, which is 1 over gamma. And like more or less always, a positive or a major outbreak is possible if and only if this basic reproduction number exceeds 1. So this is the epidemic model without contact tracing that I will be considering. So are there any questions about that? Okay. Okay. It is known that sort of when you analyze this model stochastically, when n is large in the beginning, since more or less everyone is susceptible, it's very unlikely that you happen to have a contact with someone that has already been infected. So it means that beta is actually the rate at which you infect new individuals, since nearly all of your contacts are with susceptible people. So any infectious person in the beginning infects at rate beta and recovers at rate gamma. So if you replace the word infect and recover by giving birth and dying, you're in the regime of a Markovian branching process, which is also a birth and death process. This is known to happen with large probability as n tends to infinity. So the epidemic behaves like a branching process or a birth and death process, a linear birth and death process. Birth rate beta and death rate gamma. And quite a lot is known about branching processes, so you can compute what's the probability that we have a small outbreak in the epidemic. That would correspond to what's the probability that my branching process goes extinct, or if you prefer, what's the probability that you have a major outbreak. That's the same thing as the branching process explodes beyond or grows beyond all limits. And you can also compute what's the probability that exactly 5 people get infected. That would be what's the probability that my branching process has total progeny 5. So you can do those things. And by beginning, I'm a bit vague, but one possibility is to define the beginning as up until square root of n people have been infected. So not a big fraction, but a large number. So now let's go to the first case with manual contact tracing. First of all, in order for contact tracing to happen also in reality, you must test positive. So not everyone tests positive. Some people recover without reaching the authorities, the public health agencies, and those people are not contact traced. For that reason, we look at a situation where an individual can stop spreading either because they recover naturally, and we say that happens at rate gamma, or if they're diagnosed at rate delta. I don't know if these words are correct, but you can think that at rate gamma, you don't reach, you sort of stop spreading and don't reach the authorities, and at rate beta, you stop spreading because you have been diagnosed positive and you have been isolated. Sorry, delta, did I say something else? Okay, yeah, delta. So delta is the rate at which you're diagnosed, delta for diagnosed, and gamma natural recovery. And those people are not contact traced. Of course, the more you test, the bigger delta gets, but also some people go to the testing themselves without the, yeah. So this is not really contact tracing. Adding this diagnosis is not contact tracing. And if you also have this risk of being diagnosed or chance of being diagnosed, the reproduction number is then beta times either of these things event happens. So it's beta over gamma plus delta. So I will actually call this my basic reproduction number, even that, of course, the more you test, so maybe it shouldn't be called the basic reproduction number, but this is anyway without contact tracing. So I will compare what happens if we introduce contact tracing in relation to this situation where we do diagnose people, but we don't contact trace.
Do the diagnosed people, are they taken to another compartment?
Yes, you can think of them that, that's a good question. So both stop spreading, whether you, so you either go here, here you are naturally recovered, and here you're diagnosed. And here is infectious, and here is susceptible. And if you end up here, well, I haven't started, but here we will contact trace those people. That comes on the next slide. But here you will not be contact traced. So it's you have the two options, and of course, the more testing you do, the bigger fraction will end up here.
So they are both losses out of the I classes.
Yes,
One goes to R.
they here. Well, here you have recovered, so you're immune. Here you're diagnosed, and we treat them as then you're isolated and you don't, so you stop spreading. That's a good.
Very good. Very good.
Okay. So now, how about the manual contact trace? Manual contact tracing. An individual who is diagnosed, so an individual that comes here is instantaneously, I said this problem with a model that there is no delay in the model. Instantaneously, the person is questioned for its contacts, and maybe you have had 5 contacts, and then the model says that each of these contacts, we manage to successfully reach them, test them, and isolate them with probability P. So P is sort of that is a model. So the model parameters: transmission rate, recovery rate, diagnosis rate, and this P. It's the probability or the fraction of the contacts that are successfully contact traced. Yes.
So right now, you're talking about at the beginning, so my question's not entirely relevant, but say that I have had a contact with you, but I didn't actually transmit to you, but you got named, but somebody else has infected you. That's not a likely thing early in the epidemic, but do you have thoughts on whether you're thinking about you as then being somebody that might get tested, or is it just people are actually infected?
Yeah, so later on in the epidemic, that's something you have to deal with, and I don't have it on top of my head, but there is a mathematically tractable choice,
Okay.
which is not the same as the realistic choice, because what is it? You could be named by someone who you did not infect or something, and that would of course happen. Maybe I was infected already, but later I had a close contact with someone, so the person didn't really infect me, but I had a close contact with them. So that's why it makes it much harder to analyze later on in the epidemic, and that's why I said that is the reason why we haven't analyzed the main part of the epidemic.
And is there a possibility of me naming the person who infected me?
Yes. Yes. So all, actually all contact, but of course, a contact with someone where there was no transmission going on in the beginning, that those people will also be tested, but it will have no effect. Yes. So you contact trace both upwards and downwards. Forward and backward.
So once you're diagnosed, you're immediately quarantined?
Yes, you're isolated. Yes.
So in the model, since you start from one infection, in the extreme case where P is equal to 1, at the first diagnosis, you catch everyone who is infected, right?
Yes, I think so. But that also depends on the specificity and sensitivity of the tests that you run.
Okay, we have not considered this P. Maybe the specificity and sensitivity is captured in P, but the question was if P is equal to 1, so you contact trace all contacts, then it's a correct comment that then you would.
Then you go all the way to the root.
Yes. Yeah.
For most diseases, probably that's okay, but I think for COVID, which has.
I think for all models, P is not P is never even close to 1.
Yeah, the reason I was saying COVID is that because we have this pre-symptomatic and asymptomatic, so you take their blood sample, you test them, you don't be able to detect them. They just got infected yesterday, and they are able to transmit even though the test.
And of course, you wouldn't name. So all I'm considering is homogeneous contact. So
Yeah.
you wouldn't be able to name all the people that you have been in close contact with. So it's a correct comment, but I think from a practical point of view, I don't know if it makes a big difference, because my guess is that P is typically quite not even close to 1. Yes, yeah.
You have not quantified the number of contacts. So this is included in P somehow.
The number of contacts.
Yes, that you are declaring.
Well, if you have contacts at rate beta, so when you're diagnosed, you might have had 7 contacts, and then you were infected by 1, so that's an additional 8 contacts, and then each of them you reach with probability P.
So P is the probability that each contact is indeed
I name them,
yeah, is
and they
named
manage to find the person, and they test the person. Yeah, so it includes everything. Yes.
I'm not sure about this comment for P equals 1, because you still have the gamma rate. So what just happens is with some probability delta over delta plus gamma, you sort of this. So so this will just reduce your probability of an outbreak, but it will not completely suppress it, because it could just if R naught times gamma divided by gamma plus delta is still smaller than 1.
He's got, if he tests positive, including the recovered.
Yeah, we also, if you find someone that has recovered, you will also contact trace them.
Yeah. How do you know that? I see that.
I said this in the beginning. I said it's not fully realistic, but there are antibody tests. So it's not the. Yeah, we would like. My guess is that you would contact trace those that are currently infectious, and probably those that recovered 1 or 2 weeks ago. But probably you will not contact trace someone that was infected 2 months ago.
I mean, this now stuff. So you couldn't. So if you instead just would contact trace those which were diagnosed, you couldn't otherwise. That would seem.
So contact tracing those that are diagnosed is completely useless, because they have already been diagnosed.
It's already been contact trace.
No. So if you they're friends. So it would seem more realistic to me to just say, okay, if I recover, okay, you never see me, because I mean, in particular these days you have home tests and stuff. But even before, it's sort of, if people recovered, they wouldn't go to the doctor. I mean, they just, if they're spontaneous to recover, it's unlikely you will ever be able to contact trace them. So if you instead had a model where you say, okay, if you go to the recovered state to your delta, due to the delta process, I contact trace. If you go due to the gamma process, I don't contact trace. Because otherwise I don't even know why you.
Okay, but
It's only if you
we
get
cannot
tested.
discuss too much. But suppose you infected me today. In 2 days from now, you recover, and in 5 days from now, I test positive. To me, it's not completely unrealistic that I would name, yes, I had close contact with Chris 5 days ago, so let's go and test him. And then if you test, yes, you have recovered, but you were infectious 3 days ago, so why not iterate the contact tracing?
I see. Okay.
But maybe that would not be the case if you found some that was infectious 2 months ago. Maybe you would not iterate that. I agree, but it's not completely unrealistic.
Okay. That's right.
All right. So I will sort of come back how we analyze this model. But now, so this was manual contact tracing. Now I will say how we model digital contact tracing. And as you know, I don't know how it was in the US, but some countries introduced an app which sort of recorded who you were. I don't know exactly how the definition was, if you were close enough to each other for 5 minutes or something like that. But I'm assuming that it works perfect. So, however, Yeah, so as before, people are either diagnosed or recover naturally. So I, just like before, I will treat this as my basic reproduction number. This is when there is no contact tracing, but there is diagnosis. But now a fraction pi of the community uses these apps and follow its instructions. The ones that use the app but don't follow the instruction, I count them as not using the app. So pi is the people that use the app and follow the instructions. And also, I assume that there is no assortativity or disassortativity in the sense that you don't mix. If I'm an app user, I don't mix more with other app users or less with other app users. Probably that could be included in the model, but I'm assuming that there's no disassortativity or assortativity with respect to app using. And the model then says that if I'm an app user and I'm diagnosed, then immediately all my contacts are instantaneously informed, and that is actually true for the app. So there is less delay in the app user. So here I don't see this as a big problem, but in the manual it's a bigger problem. And of course, they would not test immediately. They are asked to isolate and to test themselves. Of course, there is a delay before they test, but I'm neglecting this delay. And if they are if they are infectious, they would isolate, and also those their contacts would be contact traced. Their app using friends would be contact traced.
This again probability pi.
Yes. Or I mean, their friends. Each friend, you can say, has the app with probability pi and not the app yet. But if you have the app, it's with probability 1 that you're contacted. So here the model parameters are as before, but rather than p, which was the fraction of successful contact, here pi is the fraction of app users. So that is sort of a quantification of how effective this will be.
So this assumes that anyone who needed to be tested will get tested. Like, yes. Assume testing kits are available.
So sorry, diagnosis no, but contact tracing yes. It's not that everyone is tested. Some people recover naturally, and they will not be tested.
I thought people have to test at home, so that's
No, I mean this delta and gamma. It's still the situation that if you're infectious, you might recover naturally. Or you might be diagnosed, and of course, what fraction that go here depends on how much testing there is in the community. So that will affect this delta and gamma. So the rate of going up here is gamma. That's probably nothing you can do much about, but this delta is something you can do something about. So the more you test,
exactly,
the more likely is it that we diagnose a bigger fraction of the infected people will be diagnosed. And of course, that will help in the contact tracing. If no people are diagnosed, then contact tracing will not be very useful.
Okay.
So it's hard to do contact tracing.
Sorry?
It's also hard to do contact tracing.
If they're dead, yes. It's very hard. But let me note one thing, that pi was sort of a fraction of my contacts that I knew their names and maybe had their telephone numbers and that responded. But pi is now the fraction that use the app. And for a contact tracing to happen between two individuals, both these individuals need to use the app. So that's why maybe pi squared is a more natural quantity to compare with than pi, but just I'll come back to that later. And of course, you can combine the two. And just like before, we treat this R0 as both natural recovery and testing. And now an individual who's diagnosed is immediately contact traced with manual contacts. If the person was diagnosed is an app user, all the app using friends are also contact traced. So you can be, if you're an app user, there is both manual contact tracing to the non-app users, and among the app users, you have 100% contact tracing. So there you have both of these parameters.
Assume that the app is perfect.
The app is perfect, yes. So that's you could
change the pi.
yeah, I think that could be I haven't thought about that. I think that could be sort of interpreted in the pi, but maybe it should be interpreted in the pi squared. I'm not 100% sure, but yeah, I'm thinking of pi as the people using the app and following all the instructions. And of course, in reality, you would probably this mobile thing would miss the very short contacts, and you could have infection there as well. So probably we should have sort of some P relating to that as well to make it more realistic.
I'm sorry to bother you here. Yeah, we're also looking at the scenario where contact tracing can realistically, for example, we're having like 1 million new cases a day, confirmed cases a day. How do you have the required number of contact traces that can?
Yes, so that's a good comment.
Yeah.
I can save myself by saying I'm looking at the initial phase of the epidemic when they're not 1 million.
Okay, very nice.
But you're right that this assumes that you have an infinite amount of contact tracing people and so on.
Yeah. Fair enough.
Okay, so how do we analyze this model? Well, the problem with contact tracing model is that you break this independence, because in the traditional epidemic models, if I get infected, then I behave more or less independently of the person who infected me. But when there is contact tracing, that thing is broken, this independence. So you can no longer approximate it by a branching process. Well, at least we haven't been able to do that. However, we can look at sort of to be traced components and treat these components as individuals in a branching process. So for instance, if, well, one thing, think about this manual contact tracing. I said that there's a probability P that you will contact trace someone. From a probabilistic point of view, you can toss this coin P at the time of infection, and it would mean that if the person gets diagnosed, contact tracing will happen. So you can do that already from the start. So then there are two types of infections: an infection where there will be a manual contact tracing later on, or where there can be a manual contact tracing on. That's one type of infection. Another type of infection is an infection where there will not be a contact tracing event. And for those, the later type of infections, those individuals will behave independent from each other. So, so then you can sort of look at, okay, I get infected. Maybe I'm infected by someone there will be no contact tracing link. Then maybe I infect 3 people that I will possibly contact trace later. They belong to the same component, but then I infect some other people that I will not contact trace, or they will not contact trace me. They belong to new components. So within such a component, there is only contact tracing links, and outside to new components, it's non-contact tracing links. And those things will behave independently. So here's a figure trying to illustrate this. The gray means white is infectious, gray is naturally recovered, susceptibles are not in the figure, and black is if you're diagnosed. So this person was infected one person here, and the coin tossing whether to contact trace or not was decided that there is no contact tracing going. There will be no contact tracing along this link. So that's why it produces a new component. And here there's an infection, and here there will be contact tracing later on. Same here. And then this person recovers naturally, And this person infects someone, recovers naturally, infects this one, and then this person recovers naturally. This one infects someone where there is a non-contact tracing link, so that starts a new component. And whenever someone, and then by chance, this guy infected 2 people and then was diagnosed. And when this is diagnosed, the whole component is killed because this was diagnosed and there was a contact tracing link here and a contact tracing link here. So all these 3 individuals, these 2 are also diagnosed and isolated. So these components, once a new component is born, it behaves completely independent of its ancestor and the other way around. So the branching process is not for the original individuals, but for these components. So how does this component behave? Well, it starts by one person being infectious, and its infector, there was a no contact tracing link to its infector. And then it grows. So now it's we keep track only of the number of infectious people. So it can grow by 1. Here it grow by 1. If this person recovers, it decreases by 1. And if this person, and let's say here, so here it grows. It started with 1, then 2, then 3, and then this person was diagnosed. So then the whole thing was killed. So it goes up by 1, it can go down by 1 if one of the 2 individuals recovers, or it can be killed, the whole thing. And that is probably on my next slide. So if we keep track of, so S now is the time since such a component was born, and we count the number of infectious individuals in such a component. This can increase by 1. And what is the rate that it increases by 1? Well, each of those infectious individuals have contacts at rate beta, but it's only with probability P that it's a contact tracing link between them, and it's for each infectious individual. It decreases by 1 if one of the it decreases by 1 if one of these 2 people recovers naturally. This happens at rate gamma times the current number of infectious individuals. And it drops to 0 if any one of the individuals is diagnosed. So we have, it's like a birth and death process where there's killing of the whole component as well. However, as it evolves, it will also give birth to new components. And what is the rate for that? It is the rate beta times the probability that there is a non-contact tracing link, and each individual does this. So you see, it's all linear in the current number of infectious individuals. So this thing goes up by 1, down by 1, or is killed. But between each jump, it gives birth to new components. So how many, and all this happens at linear rates. So how many births of new components will there be before a jump? Well, if we have these rates, it's just, this is the probability to have a birth rather than a jump is this thing divided by the sum of all rates. So we will have a geometric number of births between each jump of the process. And the reproduction number in terms of these components is the expected number of new components produced by one component before it dies. It is the number of births of new components between each jump. And if we let n denote the number of jumps up until this process goes down to 0, we get this expression. But I mean, the true expressions in terms of parameters are a bit more complicated. But anyway, this is the general reasoning of it.
So is it, because you have this possibility of killing a whole component, you will never get an infection where a component grows to infinity. It only happens because you get infinitely many components. Or could it be that the infection survives because one of your components survives?
The component cannot grow to infinity.
Due to this, right?
Yeah, because it is killed at the positive rate. So if there is diagnosis, if there is no diagnosis, if all people recover naturally, then there will be no contact tracing. So then it can go. Yes.
So is it correct to think of this as like it's a branching process of birth-death processes almost?
Yes. It's a branching process of consider this thing as your component, and this thing it's like a birth-death process with the additional thing of a killing event.
Yes. So like each individual is kind of a birth-death process.
Yes.
It doesn't have to go to zero because at the one hierarchy of a whole process where can be killed from a branching process, that's one level above. Yeah.
Well, this thing will eventually be killed because wherever you are now, there is a positive rate of going down to zero.
Yes. Yes.
Yeah, so it's a branching process, not of original individuals, but of these type of components. So of course, over time they evolve, but we look at from the birth until this thing is killed,
right?
How many new components did that give birth to?
Component is a linear birth-death process with an external.
Yes, that is a component, yeah.
Yep.
Now, if you generate a lot of components, let's say n of them if possible, then each of them is sort of small, but the largest one will be for a log n. Right?
Probably. Yep, that would be my guess.
Okay.
Yes. I said my time, my talk will be shorter, but there have been a lot of questions, so I will spend all my time. But that's good though. So I like it. So the reproduction number, I skipped some details here, but I said that the number of jumps between, the number of external infections, so the number of new components born between a jump in this birth and death process is geometrically distributed and independent between each jump. So the total number of external infections is the sum of these geometric distributions, but it's the number of components in randoms because it's birth and death process. How many jumps does it do until it goes down to zero? So that's a random quantity which you can sort of express. So you can get an expression for this reproduction component reproduction number. And then, okay, what does this mean really? So if this is 4, what does that mean? It means that a component gives birth to on average 4 new components before it is killed. But okay, well, you wouldn't say that to sort of public health agency. Well, the component gives birth to 4 new components. They want to know what's the individual reproduction number. And then you can actually express that as well. So this component, I tried to describe it, grows like a birth and death process with killing. How many individuals on average will be born in this component? You can compute that mean. Let's call that mean mu for so this is the average number of individuals born before such a component dies. So maybe that is, let's say it's 10, or let's say it's 5. 1 person of those 5 were infected from outside, but the other 4 were infected from inside. So the number of internal infections is mu comp minus 1. And how many external infections? Well, that is actually this reproduction number. So if this was 7, it means that 7 new components were infected from outside, but these are actually 1 person in each time. So the total number of infections produced by such a component is external reproduction number plus the internal number of infections. And well, and then if we divide by the mean size, we get an individual reproduction number. And this is not, we had a, oh, it should say reproduction number. This is not the true basic reproduction number, whatever that means. We had this short discussion about that last week, but it is a reproduction number, an individual reproduction number, in the sense that whenever this is bigger than 1, this is bigger than 1. So this is a more natural reproduction number, I would say. So this is how we did in the manual contact tracing. With the digital contact tracing, it's not the same, because now we actually have 2 types of individuals. We have the app users and the non-app users. The app users, they infect non-app users. That would be a new component, because if an app user infects a non-app user, there will be no contact tracing. But if an app user infects another app user, that will belong to the same component. And if you are a non-app user, you can infect another non-app user, so that's just another individual. But you can also, if you are an app user, you can infect, sorry, if you're a non-app user, you can infect an app user, and that will start a new component. So here it's a 2-type branching process. One of the type is such an app using component, and that will grow and die more or less like this component that I talked about earlier, not exactly the same, but in the same spirit. But the other individuals are the non-app users. So these are individuals, but these are components. Here is an illustration of it. Circle is an app user. So an app user infects another app user, that is in the same component, but here an app user infects a non-app user. That's just an individual of itself, and this app user infects, sorry, this non-app user infects another non-app user, and then is diagnosed. If this person is diagnosed, nothing happens. So it's maybe not pedagogical, that's a black box next to it. But if this is diagnosed, it has no effect except that that person stops spreading. This non-app user also infected an app user, which starts a new component. And by chance, this person was diagnosed. And when this person is diagnosed, the whole component is killed. I will go in less detail here because I want to move on a little bit. So here we have a 2-type branching process, and we try to compute the next generation matrix. And the hard one is this one. This is an app using component. How many non-app user does it infect during all of its life? That you do in a similar fashion as before. And the reproduction number is then the largest eigenvalue to this matrix. And then for the to be traced components, I will just go to the figure here, I think. This is an app user. If an app user infects, so here a dashed line means that there is no digital contact tracing or manual contact tracing. Here an app user infects a non-app user, so there could be a solid line. For instance, here is such a solid line. No, sorry. Here is such a solid line. So this means that the app user infected a non-app user, and there will be a manual contact tracing, but here there will not be a manual contact tracing. So for that reason, it creates a new component.
Is it black box or not?
Sorry?
Non-app user.
Look at your
Something wrong.
Your first line there says that the circles are the app users.
Probably that's incorrect then.
I don't see anything there. One way or the other.
This is a non-app user.
Yeah.
Yeah, this is a non-app user.
I think it doesn't matter. The only dash lines you have are between circles and squares, so.
Yes,
But I
I mean,
agree, can't
that's
tell the difference.
the only between non-app use. Sorry, between circles, there will always be a solid line. But here there could be a digital. Here there could be a digital. Sorry, a dash. Maybe the figure isn't very clearly, but anyway. So we have one component, but there is one difference here. This one is started by a non-app user, and this one is started by an app user, and they will actually have different properties. So the type here, we still have a two-type branching process, and the type is defined by who is the index case. Is it an app user or is it a non-app user? They will have slightly different distributions. And you compute, just like before, the next generation, well, just like before. It's a bit complicated, but I will not go into how that's done. And the reproduction number is the largest eigenvalue. Okay, so that is how we analyze things. And now let me show some numerical illustrations to see if we learned anything from it. I think we learned a little bit, but let's see. Let me point out that in all the models, contact tracing is initiated when someone is diagnosed. I mean, if this one is 0, contact tracing doesn't help. So, and the bigger this is, of course, the easier, the better will the contact. So what is the probability of going here as opposed to here? That is delta over gamma plus delta. So I will see how effective are these methods as a function of the probability of going here and as a function of this pi and as a function of this p. That's what I will show. So on the next slide, I will have a heat map of the component reproduction number for manual as a function of the diagnosis probability and this p, which is the fraction of contacts that are successfully contact traced. So yellow means a large reproduction number and blue means a small reproduction number. And here I think the value 1 goes. Beside that it looks like a nice sunrise or sunset, it's very surprising that if you fix this probability, here is very surprising situation. So you fix this probability, so you have a fixed probability of being diagnosed rather than naturally recover. And then we improve contact tracing. And the reproduction number grows. How could that be?
Detect more, identify more cases.
Yes, but you would expect the reproduction number to decline then, of course. The more people you detect and contact trace, you would expect a decline. Sorry?
Isolate people who are contact traced.
No, but what do you think is better? If P is, so if you reach 20% of your contacts and contact trace them, or if you reach 50% of your contacts and contact trace them, you would think the contact tracing is better if you reach 50%, so you would expect the reproduction number to decline. But here it goes the other way around. And why is that?
Is it some herd immunity effect?
No, it is that we are considering the component reproduction number, and that's a different thing, because this means that a component, the number of new components produced by one component actually does increase, but on the other hand, the size of a component decreases. So this reproduction number is not relevant for public. We should look at the individual reproduction number as well. And that looks the way as one would expect. So that was because we started doing this. And I said, this can't be true. So we looked in the code, did we do everything right? Is the branching approximation correct? Blah, blah, blah. But then finally we realized that, okay, but it's that we should instead look at the individual reproduction number. And then we see this, it should decay in this direction because the more people we diagnose should reduce the reproduction number. And it should decay in this direction because the bigger fraction that we managed to reach in the contact tracing, that should reduce the reproduction number. And it did when we looked at the individual reproduction number.
Both of them being equal.
Yes, so that's an important thing. Both are thresholds in the sense that if they're lower than one, we will not see outbreaks, and if they're bigger than one, so that's a good comment.
So
did
you assume, sorry, go ahead.
So that must mean that when you're looking very near to this threshold, it must be different because it can't be that one of them is drawn below one and the other above one.
You're right, but I didn't exactly follow your argument, but I'm sure you're right. But it's hard for me. Standing here on the stage, it's hard to me to follow, but I'm sure you're right. Let's go to the digital one. How effective is that? Now my time is up. How is effectiveness? Well, we wanted to compare it with manual, but let me stress that this P is maybe, the two models are quite different. So why should we compare P with pi? Maybe we should compare P with pi square, whatever. But we did compare with pi. And what is this? The axes are wrong, but maybe you can imagine that there's an axis here, invisible axis. So this is, the problem is that we cannot compare the reproduction number because for the manual, we had two reproduction numbers, the component and the individual. But if you remember, for the digital, we had a two-type branching process. So the reproduction number there was the largest eigenvalue. So if that is 4, should we compare that with this one being 4 or that one being? They're hard to compare. So instead, we looked at, like Chris said, we looked at when is criticality reached. So these curves is when criticality is reached. And this is for the manual contact tracing. Here is this tracing probability. And here for the manual, this is P. So we see that suppose we 50% are diagnosed, it means that P has to be as big as, sorry, I forgot what was beta. I think the original R naught was 3, if I remember correctly. So it means that if 50% are diagnosed, we have to find approximately 80% of the contacts in order to, so we are subcritical above the curve and supercritical below the curve. Whereas for pi, we would have to have a much higher usage of apps, so maybe 90%. If we did the same plot, but instead of plotting pi, if we plotted pi squared, the two curves would be closer to each other, but they would not be identical. I forgot to bring that slide, but they would become closer to each other, but not identical. Finally, how about the manual and digital? Well, it's sort of hard. What should we compare with? Well, one thing we thought of, one would guess that the two effects would act independently. So let's say that if the manual contact tracing reduced the reproduction number by 50%, and the digital on its own reduced it by 50%, one would guess that maybe the combined model would reduce them by, what is it? 75%, yeah. So we compared the effect with the situation, with the naive guess that they would act independently. So that is what we compared. So if they acted independently, if this is the reduction in the reproduction number, one would guess that the remaining part is similar to the remaining part if they acted independently. On the next slide, we plot the critical combinations of P and pi for this thing to equal 1, and the critical combinations of P and pi for this thing to equal 1. And here are the curves. So this is the line, critical line for the combined model, whereas here is the critical line if they would have acted independently. So it means that here, if we did not have this model, if we did not analyze the combined model and guess, let's assume that they act independently, we would assume that we are super critical here, whereas in fact we are subcritical here. So why is that? Well, the reason is that if you are manually contact trace, that will shorten your effective infectious period, which will also have an effect in the digital contact tracing situation. That's as much as I can say. But if you're manually contact trace, it will shorten your infectious period. That will also help if you were an app user, you would infect, you would then be diagnosed a bit earlier. I don't know if I'm able to explain that well enough, but they do sort of help each other in some sense, which is illustrated in this figure. So this is now the end of the talk. And what are the conclusions? Well, we were able to analyze, given these shortcomings in the model, we were able to analyze manual, digital, and combine using different types of branching process. The reproduction numbers are not for the original individual, so they're harder to interpret, but we, in some situation, we could define an individual reproduction number. And the combined model has a better effect than if the two type of contact tracing acted independently. Right now, we are focusing on adding a delay between the diagnosed and successful manual contact tracing. The problem is that this limiting branching process will be of a continuous type. So you have an infinite number of types and a continuous type space. So that makes it harder to analyze, but that's what we are doing right now. And that's it. Thank you.
Presentation of any questions? I know it's break time, but we've been interrupting you all, but I like the interruptions. Any questions? Yes, please. Go.
So the results you're seeing about the two sort of being synergistic, the two different test types, not being independent, or tracing types, I mean. I'm curious if you just treat it as one type. What I'm wondering is basically, should I think about, would I be able to see the same kind of non-independence if I think about it just as we're doing contact tracing and then we improve the quality of our contact tracing, our manual contact tracing? Those, I feel like those I wouldn't necessarily expect to be treated as independent events. So I'm.
You mean that first you had
you just add an extra manual,
and then you added,
it's
not a linear.
Yeah. So that one, it doesn't surprise me that that's not independent. So I'm now wondering, maybe sort of the intuition that these two would be independent, if it's kind of the same reason that breaks, and it's way outside my intuition at that stage.
Yeah. Possibly that is a good explanation to why we're not doing that.
Okay. Yeah.
Thank you. Very interesting and nice talk. So I have now, if we wanted to actually analyze what happened in the real world, we would want to take into account that eventually they're less susceptible. So you would want to prove some kind of law of large numbers. So maybe in this case it would be a functional law of large numbers, because
you're talking about I focused on the beginning, but you meant later on in the epidemic, or?
Yes, let's see. So, I mean, you predict this small outbreak, but maybe you would like to understand that a large outbreak actually needs you at least increase epsilon n many people, which would need to control a little further. So maybe write down. I don't think you can do a differential equation because effectively your blocks will not die in exponential time setting. So you probably will have to write a different equation and try to do the central.
Yeah, but the thing, the more crucial thing is, I think Joe will mention this in the beginning. So later on in the epidemic, you will be named in these contact tracing procedures also by people that you were not infected by. So maybe I was infected by you today. And then tomorrow, Joe will have an infectious contact with me, which I was already infected, so it had no effect. And then 2 days later, Joel is diagnosed. So would he name me? If the answer is yes, the contact tracing will happen between contacts that will not result in infection. That is sort of not contained in my model.
Yeah, so you could be named because I named him, even though you were the infector. And
yeah, so in reality, Joel would name me. They would test me, I'm infectious, and I would name you. But still, I was not infected. Now I forgot exactly what I said, but I was not infected by you, Joel. I was infected by you. So it's this naming thing that becomes more complicated.
But maybe it gives a boundary for information. Helps.
Yeah,
if your branching process predicts there's an epidemic, maybe in real life, this is stochastic dominated or dominating.
Yeah, it could be. But you could get some domination, it could definitely be the case.
So a lot of this depends on how people behave.
Yes.
Most people have seen not trust their social careful all the try to stay in isolation. But sometimes economics play a role. I cannot stay in isolation because I have to work. And, it's how the case of the big factory workers. Some of them are told that they have to say something. So that too. So what's the impact of human behavior if people choose? Of course, we don't have this assumption that humans behave the right way to minimize the relation in cases. But it's suppose I could see with other diseases, for example, with HIV/AIDS in the 80s, people say, well, this is a life sentence for me when I got infected. Why do I have to care about other people? Let me just go and transmit as many people as possible. So what's the impact of human behavior saying infected is not necessarily humans, all humans behave the right way.
Yes, so I think some things can be included in this module, like maybe Jan mentioned this in the digital contact tracing. Perhaps these apps don't manage to catch all the contacts, so maybe you can sort of say include one parameter saying that we miss some of the true contacts because the apps, you even if you're close to each other and infect each other, maybe you were only close to each other 30 seconds, and that is not recorded. So I think that could be included in this model framework, but a much more harder thing to include is if the behavior changes with time. So maybe I can save myself here that I'm only focusing on the initial phase, but and then maybe behavior is more or less the same, but of course later on people get tired and following this. So over time you should probably make these things, the fraction obeying the instructions decline and stuff like that, and we haven't considered that.
It will stop here and go to break, but Dongni, please. Start the workshop with this fantastic topic. Or break time, I think you're going back at 11.